Hey, the main topic here in section 4.2 is the mean value theorem, a theorem I really like. So recall in the previous section, we learned about the extreme value theorem. The extreme value theorem stated that if your function f is continuous on closed interval ab, then it is a guarantee the function f has an absolute maximum and an absolute minimum. And again, the extreme value theorem was an example of an existence theorem. So to motivate our next existence theorem, let's head to the chalkboard. Got a misspelled word there. But I'm going to head to the chalkboard to motivate the next existence theorem. All right, here we're going to motivate our next existence theorem. And let's check out this graph I have over here. It's a graph of some function. Don't know what the function is. Don't care. So let's make some observations about the function just from the graph. The first observation that I would make is that it's continuous. So the function is continuous. And we have a closed interval AB. Let's see, what else do we notice? Well, it looks like, let me get bigger so I hit it. It looks like f of a is d, and f of b is also d. So f of a is d, and f of b is d. Okay, on the open interval AB, the graph doesn't appear to have any sharp turns in it, so I'm going to say it looks like the function is differentiable on the open interval AB. Well, folks, if you have a function that's continuous on the closed interval AB, such as this, and it's differentiable on the open interval AB, such as this one is, and f of a equals f of b, which this one does, then our next existence theorem is going to say that if there's a guarantee, if you satisfy these conditions, there's a guarantee that there's at least one number, c, that's in the interval AB, such that f prime of c is 0. And notice this one would actually have two values of c. But our next existence theorem says that it's going to be a guarantee that there's at least one. So let's head back to the slides and formalize what this next existence theorem is. It's called Rolle's theorem, and this discussion was meant to motivate what Rolle's theorem says. So let's go back to the slides. All right, so here's what the motivation at the chalkboard, this next existence theorem is called Rolle's theorem. So here's what our work at the chalkboard told us. If your function f is continuous on closed interval AB and it's differentiable on open interval AB, now keep in mind saying it's differentiable on open interval AB, that just means for all values in the open interval AB, the derivative exists. So that means there would be no sharp turns, for example, in the graph. If f of a equals f of b, then there exists at least one number c in open interval AB such that f prime of c is 0. So it tells us there's at least one number c in open interval AB where the graph of the function has a horizontal tangent line. And, well, that's the moral that I have here. So let's look at a quick example. So for the functions that you'll see below, on the indicated interval. And part 1 will verify that Rolle's theorem applies. Then in part 2, we're going to find all values of c guaranteed by Rolle's theorem. So the first one, part A, we're looking at the function x squared minus 3x plus 2 on the closed interval 1, 2. And in part B, we'll look at cosine x on the closed interval 0 to 2 pi. So folks, you know the drill. Write this down. Get these both of them written down because I'm going to head off to the chalkboard to work through them. All right, in this example, for each function, you were asked to do two things. The first thing, verify Rolle's theorem applies. And the second thing, find all c guaranteed by Rolle's theorem. So the first function, f of x equals x squared minus 3x plus 2. It is continuous on the closed interval. It is differentiable on the open interval because it's a nice polynomial function. And f of 1 does equal f of 2. So we're just going to go ahead and jump to part 2. Find all values of c guaranteed by Rolle's theorem. So that means Rolle's theorem says that there is a c such that f prime of c is equal to 0. So we have to get the derivative. So there's the derivative. So technically speaking, what Rolle's theorem says is there is a c such that f prime of c equals 0. Well, f prime of c, well, we put c in here. That's f prime of c. So f prime of c equals 0 at c equals 3/2. So when you look at the answers in the back of the book, they may list it as c equals 3/2. If you told me x equals 3/2, I wouldn't be upset with that. But that's it for part A. Part B. Function is cosine x on the interval 0 to 2 pi. So the conditions, the preamble of Rolle's theorem, if you will. Cosine x is continuous on the closed interval AB. It is differentiable on the open interval AB, 0 to 2 pi. And f of 0 equals the f of 2 pi. F of 0 is 1, f of 2 pi is also 1. So now we can do part 2, apply Rolle's theorem. So we get the derivative. We know the derivative of cosine is negative sine. So technically speaking, following the spirit of exactly what Rolle's theorem says there is a c such that f prime of c is equal to 0. So negative sine c equals 0. Multiply both sides by negative 1, and we get c equal, and keep it again. If you just took this and set it equal to 0, and you had x's instead of c's, I'm fine with that. I'm not going to mark it wrong. That's okay. So where does sine equal 0 on the interval 0 to 2 pi? Well, it's 0, pi, and 2 pi. However, our answer here is only one of those three. Our answer is only c equals pi. And that's because Rolle's theorem says these values of c are in the open interval a to b. So it'd be the open interval 0 to 2 pi. 0 and 2 pi are not in the open interval, they're in the closed interval. You know what, just to practice Rolle's theorem real quick. In section 4.2, go to the exercises and do number 12. So pause the video, do number 12. After you've done it, restart the video, and I'll be here at the board working through it. All right, folks, the first thing I would verify is that the function does satisfy all the conditions of Rolle's theorem, and it does. It is continuous on the closed interval 0 to pi over 2. It is differentiable on the open interval 0 to pi over 2. And f of 0 does equal the f of pi over 2. So Rolle's theorem says that it's a guarantee that there's a c in the interval 0 to pi over 2, the open interval 0 to pi over 2, such that f prime of c equals 0. So we need to get the derivative. So the derivative. Well, we know the derivative of sine is cosine 2x, and then remember the chain rule, the derivative of 2x is 2. So it seems like we've been dealing with this quite a bit lately. got to solve a trig equation, divide both sides by 2. And, you know, where does cosine equal 0? Let me, if I cover that up. What needs to appear behind my hand so that we get a true statement? Well, pi over 2, 3 pi over 2. So that means 2x must equal pi over 2 and 3 pi over 2. And then technically speaking, I need to make a second trip around the unit circle because of the 2. So let me go ahead and just write that in here. And then you divide each of these by 2, so you get x as pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. But we're looking for values of x, or what the book would probably say c, in the interval, the open interval 0 to pi over 2. These are not in the interval 0 to pi over 2. So the only one that is an answer is x equals pi over 4. All right, folks, let's head back to the slides and see what's coming up. All right, Rolle's theorem, not too bad. So next up is yet another existence theorem. To understand this next existence theorem, I'm going to head back to the chalkboard and we're going to motivate what it is. So here I go to the chalkboard. All right, hey, to motivate what this next theorem's all about, let's take a look at a graph of a function over here. Don't know what the function is, I don't care. I have the closed interval AB. I've labeled, this is the point A, f of A. That's the point B, f of B. Some things I kind of observe right away. The function is continuous on the closed interval AB, and it's differentiable on the open interval AB. Now, if I do the following, let's see here. Let me get the blue chalk. If I draw a line through those 2 points, well, that line has a name. Remember, it's called a secant line. And remember, a secant line gives us an average rate of change. So let me just write that down again. I'm going to abbreviate average rate of change as AROC. Average rate of change, slope of the secant line, and for this situation here, the slope of the secant line, well, it's just the old slope formula, f of b minus f of a over b minus a. All right, now watch what I'm going to try to do. This is important. I have to demonstrate it, and I'm going to do my best, but see if you can figure out what I'm trying to do. Let's see, so about right here. All right, did you notice I was trying to draw a tangent line that was parallel to the secant line? Remember, tangent line gives an instantaneous rate of change, which I'll call IROC. And we know an instantaneous rate of change is given by the slope of a tangent line. Well, I don't know what the function is, so I can't compute its derivative, but I can arbitrarily say, let me just generically call that x coordinate, let me call it c. The slope of that tangent line is given by evaluating the derivative at c. So now, what do you know about parallel lines? That's right, parallel lines have the same slope. So this is the foundation for our next theorem, which is called the mean value theorem. And I'm going to say more about it when we get back to the slides. And I'm even going to mention this when I get back to the slides, but I'm going to mention it here as well. If you've ever received a speeding ticket and it's been in a speed trap area, you've been hit by the mean value theorem of calculus. Because what the mean value theorem also says, besides geometrically, tangent line parallel to the secant line, it also says in terms of rates of change, average rate of change equaling an instantaneous rate of change. So if you're going down the highway and you pass a highway patrol, a person who's off the side of the road, and say a minute later you pass another one that's on the side of the road. I mean, if they know their distance apart, if they know how far apart they are, let's say they know they're a half a mile apart, and they clock you traveling that in a given amount of time, they can do a quick division to get your average rate of change over that distance. The mean value theorem will state that there was a point in that trip where your instantaneous rate of change was equal to the average rate of change. But we have all the pieces here to motivate the mean value theorem. So it's time to head back to the slides and officially write down the mean value theorem. All right, so here's what we motivated at the chalkboard. Did a lot of discussion. This is the theorem called the mean value theorem, which I tend to abbreviate MVT. So our preamble to the theorem. If function f is continuous on closed interval AB and differentiable on open interval AB, then there exists at least one number c in the open interval AB such that f prime of c equals f of b minus f of a all over b minus a. Here's how I remember this. I just remember it conceptually. The mean value theorem states, well, the first thing it states is geometrically, there's a tangent line that's parallel to the secant line. I mean, f of b minus f of a over b minus a, that gives us the slope of a line through 2 points, so it gives us the slope of a secant line. F prime of c is giving us the slope of a tangent line at a particular value, specifically at c. And the equal sign is saying the slope of the tangent line is equal to the slope of the secant line. Well, tangent line slope equaling secant line slope, we know from way back when we learned about lines, if two lines have the same slope, they are parallel. I also remember this in terms of rates of change. Since secant line slope gives us an average rate of change, and tangent line slope gives us an instantaneous rate of change, the mean value theorem simply says there is a value c where the instantaneous rate of change is exactly equal to the average rate of change. And I'm mentioning here again that some speed traps are predicated on this. They can, you can be clocked over a distance, any given distance, to see how long it takes you to travel the distance. That gives you your average rate of change or your average velocity over a given distance. And if your average velocity over a given distance is greater than the posted speed limit, the mean value theorem guarantees there was some point over that given distance that you were traveling exactly the speed of your average velocity. It's not cool. So let's look at a quick example here. We're going to look at the function x cubed minus x squared minus 2x on the closed interval -1, 1. Part A, we're going to determine if the mean value theorem applies. And if it does, we're going to find all c that are guaranteed by the mean value theorem. So you know the drill. Write it in your notes. I'm heading off to the chalkboard to work through this example. All right, folks, in this example, there were two parts. This function is given on the closed interval -1, 1. Part A was, does the mean value theorem apply? So the preamble for the mean value theorem, is the function continuous on the closed interval? It is, because it's a polynomial function, which is continuous. Polynomials are continuous everywhere. Is it differentiable on the open interval? And it is. It's differentiable. So I'm just looking now at part B. We're going to find all values of c that are guaranteed by the mean value theorem. So again, I'm going to come over here and write down again the mean value theorem. The mean value theorem says f prime of c is equal to f of b minus f of a over b minus a. Remember, that is saying nothing more than slope of the tangent line is equal to the slope of the secant line. That's all the mean value theorem is really saying. So I start off by finding the slope of the secant line. It's just a line through 2 points. So I'm given my interval, so I just need to find the slope of the line, that goes through the 2 points where one point has an x-coordinate of -1 and the other point has an x-coordinate of 1. So I evaluate the function at -1, and when I evaluate the function at -1, I get 0. I evaluate the function at 1. When I evaluate the function at 1, I get -2. So the slope of the secant line, and it's this part of the mean value theorem, is nothing more than -2 minus 0 over 1 minus -1. That's a -2 over 2. So that's -1. So we have found the slope of the secant line, the average rate of change of the function on the closed interval. All right, so now for the instantaneous rate of change, we need the derivative. So next we get the derivative. And the derivative is a 3x squared minus 2x minus 2. Now we want to find, technically speaking, the mean value theorem says you want to find all c such that f prime of c is equal to whatever the average rate of change is, whatever the slope of the secant line is. But we want to find, so I don't care if you call it c or you call it x. That's irrelevant. You want to find where the derivative, I'm going to leave it as x's, where does it equal -1? You're finding those values of x where the slope of the tangent line will equal the slope of the secant line. You're finding those values of x where the tangent line would be parallel to the secant line, where the instantaneous rate of change is equal to the average rate of change. So I just take my derivative, set it equal to -1 and solve, so I have to add 1 to both sides here. And I think we get this to factor pretty friendly. I think it factors to a 3x plus 1 times an x minus 1. Set each factor equal to 0, and we get x is -1/3, and here we get x is equal to 1. The only answer, though, is x equals -1/3, because we're talking about values that are in the interval. It's an open interval, -1 to 1. 1, that's part of the closed interval, but we're looking in the interval -1 to 1, parentheses around both. So I'm going to have you do one real quick. So in section 4.2 exercises, let's try number 30. So pause the video, try number 30. When you're done with it, I'll be here at the board working through it. All right, number 30, you were given the function f of x equals x plus 1 over x on the interval 1 to 3. And in my head, I'm also seeing this 1 over x as being written as x to the -1st. That's going to help me on the calculus part. But I start off by doing the average rate of change of the function on the interval 1 to 3. It does satisfy the conditions of the mean value theorem. So I get the average rate of change on the closed interval 1 to 3, which means I'm finding the slope of the secant line through the points. All right, well, x is 1. So if x is 1, the y-coordinate is 2. And x is 3. If x is 3, see 3 plus 1/3, that's 10/3. So the slope of the secant line is, let's see, it's a 10/3 minus 2 over 3 minus 1. And that's 10/3 minus 2. That's a 4/3 over 2. And then 4/3 over 2. Okay, that simplifies down to 2/3. So the slope of the secant line is 2/3. The average rate of change of the function on the interval 1 to 3 is 2/3. So now we need to get the instantaneous rate of change equaling 2/3. So we need the derivative. And that's where rewriting the function in this form comes in handy, because I know the derivative now is a 1 minus x to the negative second, or 1 minus 1 over x squared. I have to determine where does, for what values of x in the open interval 1, 3, does the derivative equal 2/3? Where does the slope of the tangent line equal the slope of the secant line? So I take the derivative, set it equal to 2/3. I'd subtract 1 for both sides. See, 2/3 minus 1 is negative 1/3. I'd multiply both sides by negative 1. And then I could say, well, let's multiply both sides of the equation by 3x squared. And that'll give me a 3 equals x squared. And then I take the square root of both sides of the equation, and I get plus or minus the square root 3 equals x. So the answer to this question is just x equals square root 3, because negative square root 3 would not be in the open interval 1 to 3. So that's in section 4.2, kind of a short, sweet section. So at this time you can, well, go do the exercises in section 4.2. Thanks for watching.